Good afternoon, everybody. I hope you had a very big cup of coffee and cake. It's a great pleasure to be invited here and to give a presentation and to pick up some themes that have been running through the week and sort of give you my spin on it. I'm conscious that I have rather a lot of material that I would love to talk about, and we will see how we go. And an hour is quite a long time, I think, for a slot anyway. So there's a kind of menu here. I'm going to start with some kind of review type material. I realize I've forgotten my prop. Sorry. So I'm going to talk about some experiments just to sort of remind you that this is a program on liquid crystals, and then go off and do some stuff which has little to do with liquid crystals. There'll be some theory in the middle, so there'll be some kind of picture show, and then some kind of detailed worrying about extremely simple equations. And then there are going to be two variations on that very simple equation. There's going to be a variation where we add in a nonlinear diffusion equation that couples into this Swift-Hohenberg toy model that I'm going to talk about. And then there's going to be another variation where I just bung on some additional terms into the kind of plain vanilla Swift-Hohenberg problem. And this sort of second part elements of this are joint work with some PhD students. And this last section is joint work with John Burke, who was at Boston University until recently. I gather he's taken the job in financial services. And there are various review articles available. Here's one I wrote earlier. So the first part of this, I thought I would give you this image, which is in fact this image. It's from Stephen Morris in physics in Toronto. And this is the front cover of the annual report of the Isaac Newton Institute 2005-2006, when some gentlemen in the audience and I organized a program on liquid crystals. So this is an electroconvection experiment with some shear, as we'll see in a moment. I don't think there's any shear in this picture. There's a pair of electrodes on the inside and the outside, so there's an applied potential difference. It's a smectic layer, and the colors correspond to slightly different molecular layer heights, I believe. I'm open to correction on anything to do with liquid crystals, okay? And there's a very nice instability of the crystal where you actually see some flow circulation in these little convection cells, which have a characteristic scale that is close to the spacing, the difference between the two radii. So there's lovely sort of experimental examples of a fluid instability, in this case driven by the electric field. And there have been plenty of intersection between the kind of pattern formation community and the liquid crystal community through electroconvection. I'm sure there are many other areas where interaction is possible. People like Lawrence Kramer were extremely good at getting this discussion going. So in this particular example, this is all taken from a paper by Morris and students. We have sort of schematic geometry like this. This is, I think, some results from numerics rather than from real experiments. And there are two kind of parameters. There's something that they insist on calling a Rayleigh number, okay, by analogy with thermal convection the whole time, which is proportional to the square of the applied potential. And then there's a Reynolds number, which is a dimensionless sort of shear rate applied to the flow. Okay? So I think omega is the rotation of the inner electrode in this case. And then you turn up the voltage and you measure the current as some indicator of how much convection you have going on. And you see that there's some hysteresis in the system, so the open triangles are increasing voltage and the solid triangles are decreasing voltage. This is at quite a low shear rate, okay? So you should think about a kind of sheared and possibly convecting fluid at this point. If you go to a larger shear rate, so Reynolds number now approaching 1/4, then you get a series of transitions of sort of intermediate states between the kind of quiescent state where there are no convection cells, no fluid motion apart from the applied shear, and a state where you're fully convecting up here. So these labels are probably too small to read. A, B down here, C in the middle, D up here. There's a state C and D where you have, instead of this kind of nice uniform collection of convection cells of approximately equal strengths, you're seeing a single isolated convection cell and then no motion apart from the background shear in the rest of the annulus. And then D is a state with two of these. But they're so far apart that one might think, there's an atomic object here that's worth studying. So this is a localized state, okay? For these purposes, localization means a whole load of different things to different people. And this, for me, is a kind of spatially extended periodic pattern, okay? So this is the regime of the previous talk, and then this is the kind of regime for this talk, and there must be some connection between them, and it's that connection that I'm going to explore through the next 55 minutes or less.
Slightly broken symmetry in the first two?
Yes, because this whole thing is being sheared in one direction. So counterclockwise and the other direction are not the same, okay? Clockwise. So yeah, everything has a slight sort of lean to it, which is fine. It's just a property of the particular setup and symmetry of the configuration. Okay. So the kind of motivation for all this stuff comes from Rayleigh-Bernard convection, where people like Günter Ahlers and his group have for decades produced incredibly high quality experiments for theorists to stumble over and misinterpret. And this is the kind of ideal convection picture that we're all very used to for a sort of a two-dimensional experiment that is really giving us one-dimensional pattern formation. So there's a very slight bend to this plan form. So the dark regions are fluid that is rising up, and the white regions are fluid that's falling down. And those turnovers are in cross-section eddies in alternate directions, and the flow is driven in Rayleigh-Bernard convection by having uniform temperatures applied to the lower plate and the upper plate. It's a viscous fluid in between, and above some critical driving temperature, you generate this instability where the system is trying to equilibrate the different applied temperatures and to even them out as quickly as possible, and it has to do that at a higher rate if there's a higher driving temperature difference here, and the initial conduction profile is unstable. So these localized structures turn up in a range of other fluid systems, and it's definitely worth mentioning the recent work by these guys, Tobias Schneider, John Gibson, John Burke, looking at instabilities in plane couette flow, so the kind of classic fluid transition in shear flow problem. And this is a kind of cross-section through some numerical experiments where they've followed and located where, as you increase the shear rate, you are able to form little localized structures like this. So I'm looking, X is the streamwise direction. This is a plan view with my shear going vertically, okay? And this is a cross-section in the kind of wall normal and spanwise direction, okay? So the red indicates that fluid is going away from you into the board, and blue indicates fluid coming out towards you. And you see this little localized undulation, okay? And those localized undulations come in two flavors, okay? They're either symmetric, even about the center, or they're all about the center. And when you follow them in parameter space, which here means shear rate, okay, Reynolds number, you see that there's an interesting dependence on that parameter where they wiggle around, okay? So there are, for any particular Reynolds number in this range, there's a multiplicity of these states, okay? And yet they're all kind of connected up in this bifurcation diagram. So this is a measure of the dissipation associated with each state. It's just some sort of solution measure. And then kind of extended states that are periodic in the spanwise direction that people know about are on this dashed line here. Okay? So there is a bifurcation connecting them up, and then there's this sort of intertwined wiggling plus a selection of solutions that link across the wiggles. Okay, they join a red wiggle to a blue wiggle. So there's the kind of phenomenology here that comes up in many different physical contexts. There's plenty of work in nonlinear optics. This happens to be two-dimensional, but there's plenty of one-dimensional interest as well, where you have a series of little atomic dots, and as you kind of glue these together, you can build up a uniform pattern by assembly of these dots. Okay, but whether you have one particular dot or not, they're kind of independent of each other when you're in this range. Okay, so there's a kind of range of bistability between the background state and having a dot present at some position, and that enables you to sort of build these structures, and there's some indication these might be useful for information storage. Dielectric gas discharge is a similar setup, we're looking at planned views, okay, and there are two plates, there's a very high potential difference across them, and there are little current filaments that form as a result, and so these are individual current filaments that again are atomic objects, but they kind of glue together in some set of complicated possible patterns. And when you plot experimental bifurcation diagrams for this, you see some of the same kind of phenomenology when you look at the ranges of applied voltage over which you can sustain one or more of these little filaments. Okay, so this is a 1 filament, 2, 3, 4, 5, going up here, slightly tilted, and the sort of point of this happens in the optics as well, and this is going to be something I'll come on to, why you get a little tilt, why and when you get a little tilt to this structure. So in terms of model equations, where as a mathematician one might hope to make more progress, there are plenty of exotic states available when you pick a sort of favorite pattern forming system and allow it two space dimensions to evolve in, as well as the periodic structures that we heard about in the previous presentation. There are, for various choices of equation, there are a number of possible localized structures. So again, you've got atomic objects. You can build atomic objects into little localized patches of pattern, and then you can have some things which are kind of axisymmetric up to the boundary conditions, and these demand some explanation as well, and these are kind of one-dimensional still because of the axisymmetry. There are other possibilities. So David Lloyd at Surrey has done a lot of work on this recently. There are various people very active in the two-dimensional stuff. This talk, in so many ways, will be one-dimensional. Okay? So, to sort of go right back to the beginning and assume that you know nor care nothing about the Swift-Hohenberg equation, this is the point to begin from. So it's a model equation for a Turing-type instability using a single scalar variable. So I'm going to have a variable w, which depends on one space coordinate x and time t, and I'm going to assume that my initial background state is completely homogeneous. So this would be, x would be the kind of azimuthal variable in the electroconvection problem, okay, apart from the curvature terms. And it's translationally symmetric and it's reflectionally symmetric in the easiest case. And I'm going to think about having an unbounded domain, or at least a domain that is very large compared to the structures that I'm interested in. Often numerical work replaces this with periodic boundaries. And then I'm considering an instability of that uniform initial state, which will be w equals 0, where I have a parabolic maximum in this curve of growth rate against disturbance wave number. So you test the stability of the solution by perturbing it with noise or something that contains lots of different wave numbers, and you look at the linear decay rate of these different wave number modes. Okay? And the kind of instability that I'm interested in, is one where I increase this parameter r, okay, and this parabolic maximum crosses the axis, and I have a little interval of wave numbers here where I have a positive linear growth rate. Okay? Because this thing is left-right symmetric, I plotted this against k squared because k and minus k are going to mean the same thing. So if I take this expression for growth rate as a parabolic function of wave number, okay, and I just kind of inverse Fourier transform it, that gives me a collection of linear terms that look like this. Okay, so this is the linear part of my model equation describing what happens typically in that kind of instability. Because it's only a linear picture, I know nothing at all about what appropriate nonlinear terms might be. Okay? If I pick some polynomial in W, then I can instantly see useful things that might sort of connect this view of the world to views of the world expressed earlier in the week, and say that this is a variational problem now, okay? And the dynamics that I've written down here are just given by taking the variational derivative of this free energy quantity. Okay, so whatever n is, I can just integrate that in a formal sense, and that's the contribution to the energy. And then for good choices of n, this thing is going to be bounded below, so it has a nice structure, and it might have quite a complicated energy landscape. It might have a large number of equilibrium states, but we're guaranteed to find one. Okay. But then, of course, I can easily break this variational structure by including terms that depend on derivatives in ways that we'll see later in the talk. So the kind of generic, typical, obvious choices for n are quadratic or cubic, okay? Nothing complicated. And so if I pick something that looks like minus w cubed, then this is something that sort of looks a little bit like a kind of supercritical pitchfork bifurcation. And this is generally called the supercritical case. Combinations that involve competing nonlinearities, so a kind of quadratic and a cubic, or a cubic and a quintic, where one is sort of potentially destabilizing and the other is kind of restabilizing, get a little bit more interesting. Okay, and it's these cases that we'll be concerned with primarily today. This one turns out to give us a subcritical kind of bifurcation if s squared is bigger than some magic number, okay, 27 over 38. And if s is smaller than, closer to 0 than this, then it's a supercritical bifurcation and the kind of cubic nonlinearity wins, okay? And then this one is subcritical when s is positive. So one obvious question is, where did I get 27 over 38 from, okay? And if I want to know where 27 over 38 comes from, then I need some way of zooming in and looking at the behavior close to that bifurcation point, taking the nonlinearity into account, okay? And so the obvious protocol is to think about what a weakly nonlinear reduction of this equation looks like, okay? So what does a weakly nonlinear reduction mean? Well, I'm hoping that I'm interested in structure with a wave number close to 1, okay? I'm producing pattern, it's got a length scale, we'll call that 2 pi. And then I'm interested in small amplitude solutions close to the bifurcation point, which are going to be decomposed into this amplitude A and a carrier wave e to the ix. Okay, so it's a classic multiple scales ansatz. It's the first term in an asymptotic treatment of the problem, and x is going to be a long length scale, so I'm allowing my amplitude, my envelope to modulate over a long length scale and a kind of appropriate long time scale, and that's going to give me a diffusive light balance when I put this in and I try and work out what the dynamics of A should be. Okay, so this is a kind of classic piece of handle turning to do now. Okay, so the next order correction involves some harmonics of A, and here it is. Okay, and then at third order we have something that involves kind of quadratic interactions and kind of cubic harmonics of the first mode. Okay, and then there's the kind of classic multiple scale solvability problem. Okay, where I want to retain the ordering of my asymptotic expansion or not produce kind of secular terms in my resulting solution here. And that solvability condition is a requirement that one typically imposes in order to get some dynamics on this amplitude. Okay, and the coefficient turns out to be something that vanishes when s squared takes this magic value. Okay, so this is the kind of weakly nonlinear reduction of this problem that I started with. Okay, through this decomposition into amplitude and carrier wave. That's asymptotic. It's a view of the world I used again and again in applied mathematics, but it's not rigorous. It doesn't really give me a relation between the dynamics of the equation I began with and the dynamics of this amplitude envelope equation. Here I've written down the forwards bifurcation equation, the supercritical version, just so that I can give you a sort of a little snapshot of a theorem that does some kind of guaranteeing of the relation between the amplitude equation that I've derived and the original Swift-Sternberg model I began with. Okay, so this is due to Collet and Ekman, and it's quite a while ago, and it didn't stop people doing this long before 1990. Okay, people have been doing this since the 50s, I'm sure, and calling it this. So anyway, so the idea is if you start off with kind of compatible initial data and you kind of track these solutions forwards in time, okay, then you're guaranteed a really nice property. So they're sort of the maximum value that they deviate from each other in space, one from the other, is bounded by something that looks like epsilon cubed times t to the half. Okay, and this is true for small epsilons and for t of order 1 over epsilon squared. So for quite long times. Okay, so at least for long times, I stay really pretty close. Okay, And this is the kind of result that's provable. I'm sure it's been improved since, but there's some at least quite good tracking property available. So I have some confidence that my amplitude equation is doing some things right, okay, near this bifurcation. But it's clear also that there are going to be some issues, okay, because if I take my ansatz, okay, where I unfortunately put t equal to 0, but if you replace the zeros by t's, okay, plug that into the Swift-Schoenberg equation, okay, then one deduces an amplitude equation that is sort of at leading order, the bit that I derived by multiple scales, okay, and then there are two kinds of other terms. This is exact, this line, okay, and then the blue and the red are the things that I've gone and discarded, okay, so the blue stuff I discarded because, you know, epsilon was small, but unfortunately it's a singular perturbation, okay, so that might give you a little cause for concern. And then this term doesn't have any epsilons in front of it, but it should be at least rapidly oscillating, okay, and if it's rapidly oscillating then it kind of averages out to be small, okay, but there are some issues here, and really the kind of issues that I'm going to talk about in the rest of the theory chunk can be thought of as coming from neglecting these terms. Okay, that's the kind of difference between dealing with the original model equation and then passing to the envelope equation. Okay. So just to kind of recap, for most purposes, this is a very nice equation. Okay, it's extremely simple. Constant solutions correspond to periodic structures, and I have a collection of solutions which are not just the wave number 1 solutions I first thought of. They have wave numbers close to 1 if A looks like R e to the IQx. Okay, these solutions, we can think about stability of it, and they're stable if Q is sufficiently small, and then there's an instability, there's Eckhout instability in a kind of parabola outside that. There are other instabilities, and this is sort of where Rayleigh-Bernard convection has kind of gone on and on and on, and people have worked out all these instabilities and then verified to see if they do actually take place in experimental work and so on. There's an extra phase shift symmetry that's come in here as well, which is interesting, okay, which is that there was no preferred origin in space for doing my multiple scales ansatz, and that's carried through here to a kind of phase shift in A, okay? There are other versions of this problem available because having identified a switch from supercritical to subcritical, okay, one might be interested in taking apart what happens as I make that transition, okay, from supercritical to subcritical. So I take a parameter. Here I'm working with the cubic quintic because the algebra is vastly simpler, okay, and I'm just thinking about S small, same solution ansatz, but different sets of scalings apply, okay. So if I'm mildly subcritical, then I just rescale things in a slightly different way to organize how the leading order terms balance against each other, and then I have to push the perturbation theory a little bit further, up to 5 orders in epsilon. But what's very nice is that nothing happens at the first 4, okay? So really at the 5th order you get everything coming in together, and this tells you that actually you can balance cubic and quintic against each other, okay, in this mildly subcritical case. So I have some bifurcation diagram now where I've got branches of periodic structures that are bifurcating subcritically, okay, they're constant A solutions, and then they sort of turn round at larger amplitudes, okay, and I can check their stability to, you know, modulational perturbations. So this branch of constant solutions for A bifurcates subcritically. It's this curve in the middle, okay, then it has a saddle node bifurcation, then it comes back and it's stable at large amplitude, okay. The interesting and slightly unexpected thing is that there is a secondary bifurcation from this solution. It occurs very close to 0 in a large but finite domain, and it contains solutions where the envelope is modulated. Okay, so there's a modulation which is small here, okay, and so the solutions down here, R is minus a quarter, look like this. Okay,
sorry, Jonathan, I've lost track of what L squared is. Remind.
Amplitude, integral of A squared over the domain.
All right.
Sorry, it's just some diagnostic quantity that's varying with parameter.
Yeah.
I expect it's, you know, the root mean square originally. So there's a kind of Setch-like solution here for the amplitude on this part of the branch, and then I suddenly shoot up at some kind of magic value where I get a plateau appearing, and these two parts of the front kind of break apart, and I have a kind of long level section in the middle. Okay, and this tells me something very interesting about the dynamics. Eventually, these two fronts get to the end of the domain. I'm in a finite domain for this calculation, and so I reconnect to the uniform flat solution. Okay, everything is now up at the flat solution. So if I put the carrier wave back in, I've got a little packet of modulated solutions here. Okay, which then sort of becomes a wider packet. Okay, so I have a little collection of convection cells. If you want a kind of physical connection, then think of W as the velocity of the fluid at the mid-plane of my convection experiment. Okay, so it's going up and then down and then up and then down as I pass from one convection cell to the next. And this is a little patch of localized pattern. Okay. Another way of thinking about this whole problem, because I'm only interested in equilibrium structures here on my bifurcation diagram, these are signs of eigenvalues, the pluses and minuses, are to think about having some spatial variation where at large positive and negative x I start close to 0, okay? So 0 is a stable solution down here for r negative, a equals 0 is stable. Okay, and then I sort of move away from 0 quite slowly, and I do something, okay, and then I come back to 0 over here. This is quite good having somewhere to walk to. So that kind of solution from a dynamical systems viewpoint, I can think of x as my kind of evolving coordinate, okay, and I can call that something that is homoclinic in space, okay, because I start at 0, and I do something, and then I come back to 0, okay. So if I just thought about the kind of spatial dynamics, okay, then I could call that a homoclinic orbit. And I could call this thing sort of close to being a heteroclinic orbit because it's starting close to 0 and then after large spatial variation, it's coming close to another constant solution. Okay? So the kind of the picture that we might have in mind is that I have a collection of orbits for my amplitude that are doing something like this. I've only got a diffusion equation, non-linear diffusion equation for my amplitude. So I've got something like this, and then at sort of other parts of the parameter, I've got some other kind of orbit like this. Okay, so let's just think about the top one, where I start near 0, and I come out towards some sort of constant non-zero fixed point, and then I go back. Okay. So there's a kind of spatial way of thinking about this problem where I forget the time derivative, okay, and I just think about the equation we had before. It's got 4 derivatives in x, so it's a 4th order dynamical system. It has an x goes to minus x symmetry, which is a reversibility from the dynamics viewpoint. And if I look at the eigenvalues of 0 for this, that reversibility implies that they have some structure. I have 4 eigenvalues in kind of general position, except that they're related to each other by a rotation and reflection in R negative, and they come close to each other. Okay, they hit the axis together, so I've got multiplicity 2 here, and then they split along the imaginary axis when R is greater than 1. And so for 0 growth rate, I've got a little interval in wave numbers that's unstable. And then this is called a Hamiltonian Hopf bifurcation, or a 1-1 resonance or something in the literature, and it's a bifurcation problem. So I can do standard bifurcation-y things, okay? So here are some standard bifurcation-y things. We've got a set of eigenvalues on the imaginary axis. This is the kind of canonical Jordan form for the linearization, okay? So I can do some normal form calculations and work out, this is due to Gerardios again a while ago, what the kind of general structure of my normal form should look like. So here capital P and capital Q are polynomials in these arguments. Mu is my bifurcation parameter still. And I've got 2 variables A and B because I have a 4-dimensional system, so I have 2 complex variables A and B for my 4-dimensional real center manifold. Okay, and then I have some remainder terms here. I can put this into the nice normal form always up to some finite order, tidying up terms order by order with near identity transformations. So anyway, so we have a normal form, okay, and we can analyze that. It has lots of lovely structure because it inherits various symmetry properties, which is part of the point of doing normal form calculations in the first place. So if I take these P and Q to be polynomials in the first few terms in their arguments, okay, and I plug that into here, I can do some eliminations, and magically, in a sense, end up with a very simple description of the dynamics, which is essentially this, okay? So I have something that looks like a kinetic energy term balanced by something that I will then call a potential energy, f of y is mod a squared, okay, so y is a non-negative variable, and it looks like a ball rolling in whatever this one-dimensional potential looks like, okay? It's just a polynomial in y, because I've taken a very few terms, okay? So if I look at that polynomial in y, then there are various possibilities. I'm interested in solutions which are homoclinic to 0, okay? So I want to be inside the kind of level set of solutions that contain 0, and that's a reason for taking these two constants which turn up both to be 0, so I can look at exactly that subset of solutions. And then I have a dependence on two parameters which are called Q2 and Q4. They were just coefficients of the polynomial that I had here before, okay? So they're just coefficients in the normal form. And I can then plot out what this potential in blue looks like for all the possible combinations of Q2 and Q4. Okay, so there are two kind of basic cases. There's Q4 positive, which is the picture on the left, Q4 negative, which is this picture on the right, and I can then examine where I have, possible homoclinic orbits to 0. Okay, and the shaded areas contain homoclinic orbits to 0. Okay, so I can produce a complete classification of the kinds of behavior that I'm interested in. And this shaded region over here for the Q4 positive case is the kind of the thing that we've been talking about so far, where I have a potential with a local maximum at 0, and then an equal energy point over here. So if I have let a ball roll from 0, it goes up to this side and then back again. Okay, so I have a homoclinic orbit for my spatial dynamical system. Okay, and clearly there are some differences. Okay, the potential has a different probability. So, in terms of what's happening for the original problem, okay, so this is a kind of two-dimensional reduction of the problem, okay, because it's a ball rolling in a potential well, okay. So if I want to go back to my four-dimensional problem, then it's essentially the same as this, except that this is a cross-section, okay, it's a two-dimensional cross-section through my full four-dimensional phase space, okay. So instead of having a kind of continuous flow dynamical system, I've got a map on this two-dimensional cross-section. Okay, and the dynamics of my two-dimensional map will be unfortunately slightly different. Okay, so I still have a 0 solution and a pattern solution, and they have stable and unstable manifolds. Those stable and unstable manifolds have the sort of iterative map dynamics on them. Okay, and they have this tangling possibility. So I have a little movie to show you now. It's a movie with 6 frames. Okay, so I will not run it at cinema standard 48 frames a second. Okay. Or if I can run it backwards very easily. Okay, so this is classic heteroclinic tangling between stable and unstable manifolds of saddle type fixed points for a planar discrete time dynamical system. Okay, so those intersections get formed sort of say here when I'm in the middle of the tangle. You can see that there's interesting new behavior, okay, because the unstable manifold of 0, this solid curve, now intersects with the stable manifold of 0, okay. So I had a heteroclinic, I was interested in the kind of heteroclinic nature of what was happening here previously, but actually being close to that heteroclinic connection means that there are homoclinic orbits as well, okay. So there's a whole collection of homoclinic orbits where these sort of noses push through each other, okay, in the tangle. So those homoclinic orbits are going to correspond to things that play the role of this object, okay. Those homoclinic orbits are going to appear as these noses pass through each other, okay, and they're going to exist for some region of my parameter space between this kind of tangency on the outside, and then these manifolds cross through each other, and then there's a kind of tangency on the inside there, okay, and then two of these persist all the way down to 0. So when I vary my bifurcation parameter from left to right here, I see none of these homoclinic orbits, and then very quickly a large number of these noses push through each other, and I create these solutions, these homoclinic orbits, through these saddle node bifurcations, okay? So I have a collection of wiggles that exist over some region of the parameter space, and then quite quickly they all kind of disentangle in the other direction, that direction, okay? And I lose the ball, except 2, okay? So these 2 are the kind of 1 wiggle solutions, and these persist all the way back to my original linear instability, okay? So there's a spatial version of the analysis that we did before, where I do something similar to the modulational equation reduction, but thinking of it from a dynamical systems perspective, okay? But it's 2 ways of looking at the same thing. In a finite domain, one sees a little kind of finite remnant of this behavior. So I'm in a domain for this calculation of 10 pi. These structures have size approximately 2 pi, so I get 5 wiggles on each branch. Okay, and then I filled up the whole domain with periodic pattern. This is a continuation of bifurcation diagram from my original Swift-Hohenberg equation. So these things are the full localized solutions. Okay, so I see 5 of these, and I filled the domain, so I have a periodic structure. So I reconnect back to the uniform periodic pattern. Okay, and then there's some analysis one can do around this bifurcation point in a finite domain. It's a steady state bifurcation with some dihedral symmetry group, and that shows that I should have, as in the last talk, 2 bifurcating branches. So they're kind of rolls and squares, okay, in terms of symmetry, and those are the things that kind of generate the 2 different intertwined curves here. Okay, so I've shown you 2 different ways of looking at this problem, one from the kind of asymptotic multiple scales approach, and then one from the spatial dynamical systems approach, and they are telling you the same thing. Okay, and what they are telling you is that there is some little interval in parameter space within this hysteresis loop, okay, where 0 is stable here and this large amplitude periodic structure is stable up here. There's some smaller interval in parameter space where I have these localized solutions available, and I have them essentially all at the same time, stacked up as little levels, okay, corresponding to different numbers of wiggles over that interval. Okay, so the hysteresis loop is quite big. Okay, hysteresis loop big, region of existence of localized patterns small. Okay, that's a resounding conclusion from things that we've just done. Okay, how small is small? Small in terms of this subcriticality parameter S that we kind of scaled to get into this regime where we're mildly subcritical. Small turns out to be exponentially small. Okay, which is why this is to do this properly, even kind of properly with the asymptotic glasses on, is quite a heroic calculation. Heroic calculations are often but not always done in Oxford by John Chapman. And then there have been some recent improvements by Andrew Dean and people in Nottingham. So there's a kind of wedge here in parameter space, a little cusp-shaped region, whereas I increase S, so S squared equals 0, okay, R equals 0 is this codimension 2 point that we've been expanding about, okay. There is this very thin wedge in which these localized solutions exist that kind of grows as I increase S away from 0, okay, but it's very, very thin down here. So, you know, numerically, I gave up at this point, okay, because we're in very large domains with very slowly modulated structures at this point. So this is numerical results, calculating how wide that wedge is. Okay, so hysteresis loop big, region of existence of localized solutions small. Okay, this is some motivation. There's stuff on the sun that interests people. They compute it on big computers. Okay, this is Rayleigh-Bernard convection with an imposed vertical magnetic field. It's a problem of enormous interest to people in the building directly this way through the wall. Okay, so if I could give this talk and kind of translate it into that building, the audience would increase yet further. There's a nice kind of separation here, okay, into regions where the field is very weak. So having a magnetic field inhibits convective transport of heat up from below, which is why sunspots are dark. Okay, they're dark because they're cold. Here's the region of active fluid motion, okay, and here's a region of strong field, the blue stuff, inhibiting convective transport up from below. In a very simple kind of geometry and a simple assumption on the fluid, okay, so I have 2-dimensional incompressible flow. I'm solving Navier-Stokes equation plus an induction equation. okay, one can see localized solutions that persist where the domain, my computational domain, is separated into a region where the magnetic field is very strong, okay, and then a region where there's no magnetic field, but there is a vigorous convection cell going on, okay? So this is the kind of straightened out version of the electroconvection problem, okay? This is hot underneath, it's cold at the top, with this additional piece of physics that there is a field here that likes being nice and vertical and not bent, and it also gets expelled by the vigorous fluid motion in the eddy, okay? So you can sustain a solution like this, it appears, because the magnetic diffusion is quite small, okay? So the field is only trying to come back in quite slowly, and the fluid motion here is quite vigorous, which is driving it back out again, okay? So you set up a balance in this kind of boundary layer, okay? And that means you can sustain a single localized convection cell, even though the field is very strong. So Q is a measure of the absolute value of the field squared, R is a Rayleigh number, it's a temperature driving. They're both large, but we're actually a long way kind of past the linear instability, okay? So Q should be big enough that we quench everything and there's no convection possible everywhere, okay? This phenomenon has been noted historically by various people, and there's been some recent detailed numerical work by Edgar, who's in the audience, and collaborators. So these pictures are from a PhD thesis of Sean Blanchflower, who's in the same group as I was at the time. And what he's done here is to pick a field strength, okay? So if Q is 0 on this line, okay, we've got the plain vanilla Rayleigh-Bernard problem. I've got vigorous convection everywhere, which is indicated by the light color, which is the temperature gradient at the top surface, okay? And then the kind of linear stability threshold, where I should increase Q to quench a linear convective instability, is about 1, okay? But in fact, you can sustain these localized convection eddies back to kind of, 28 or something, okay, in these units. So the kind of, it should have died here, okay, but it didn't die. It just kind of separated into a really vigorous region and a region here where there's no fluid motion at all, and there's a uniform magnetic field, okay? So I can set this up. So, okay, so there's, from that linear problem, one can do a linear instability calculation for Rayleigh-Bernard convection plus a magnetic field. One can do a weakly nonlinear convection calculation theory, okay? And Paul Matthews and Steve Cox pointed out that there is an additional feature, which is that there is this sort of diffusive-like quantity, which, because it's got a zero growth rate at zero wave number, needs to be included in your weakly nonlinear calculation. So the dispersion relation now kind of looks different. It's got these two different branches to it, okay? So this is k squared against growth rate. We've got a pattern forming instability, so we've got that piece. And then there's a kind of second eigenmode with a zero growth rate at zero wave number, okay? So that's got an amplitude given by this capital A, okay? And that couples in to your kind of activity variable, your amplitude. So the thing that I called big A before is now little a, slightly unfortunately. And these coupling terms represent the physics that I talked about, okay? And one can see that that driving, that coupling, induces these kind of modulational instabilities of the uniform pattern that weren't there before, okay? One might sort of think this is not a weakly nonlinear phenomenon, okay? These solutions look really very fully nonlinear, okay? If there's no field in here, then I've got a Rayleigh number of 20,000, okay? There's no field, so my kind of locally, my critical Rayleigh number is 657, okay? So I'm very supercritical here. This is transporting a lot of energy up from below, and the field here is very strong. So I've got sort of two parts of my solutions which are both far from this linear world, okay? So it turns out that one can do a sort of distinguished limit calculation and take as our expansion parameter this epsilon, this solution amplitude, the magnetic diffusivity itself, okay? So this is a toy problem where I've got a supercritical Swift-Hohenberg equation which describes the pattern-forming instability of Rayleigh-Bernard convection that happens in the absence of a magnetic field. I've coupled it to the field acts to damp down the flow, and then I've got a diffusion equation for the magnetic field, B, okay, which has a nonlinear coupling back to the local solution amplitude. the strength of convection locally. Okay? And this has got a conservative form because the total magnetic flux through the layer is a conserved quantity for the system. Okay? It's got various symmetry properties. One thing I didn't notice for quite a while is actually this has a variational structure. Okay? And this is very handy. Okay? Because people have been, you know, whenever there's been one of these, people have pointed it out. I thought I would point it out. Okay? For this problem. In fact, because of the kind of conservative nature of the second equation, if I'm looking just for equilibria, which I am, and I set the time derivatives to be 0, I can integrate this twice very, very quickly, okay? Remembering that the average value of the total magnetic flux through the layer is a conserved quantity, so I want the average of B in space to be 1, okay? So I do that, and I can exchange my B evolution equation for a kind of non-local, non-linear contribution to my Swift-Herrenberg equation, okay? So I end up with a Swift-Herrenberg thing here, okay, and then P is a kind of nasty integral quantity, and I've got a slightly more complicated kind of non-linearity, okay? And the non-local nature of this term changes the kind of the localized state bifurcation diagram wonderfully, okay? I can do a similar kind of weakly nonlinear calculation now in this distinguished limit where I've got small diffusivity, so I've got a small parameter already sitting here, okay? And that means, not surprisingly, that I go from a non-local Swift-Herrenberg to a non-local Ginzburg-Landau, okay? So this is my plain vanilla Ginzburg-Landau that we've seen before, and here is another sort of non-linear, non-local contribution, okay? So I can then do some bifurcationology on this, okay? Bifurcational, bifurcationology, bifurcationologist. I managed to make that word twice as long. So I have a supercritical instability, okay? And then there's a little bubble of secondary instability here where I have those modulated solutions that Cox and Matthews wrote about. As I crank up the field strength, okay, I can make this sort of modulational instability go this way before it comes, and then it goes all the way over here before it comes back, okay? So my uniform patterns are this branch. They're slightly subcritical, and then they're supercritical, okay? And these modulated things are way subcritical and then way supercritical, and then they come back, okay? So the localized solutions, from what we've done previously, are going to be associated somehow with this sort of extra branch over here, okay? So this stuff has all the same kind of structure for these amplitudes that we've seen before, okay? So they have the same collection of localized states, and in some sense what I've done is reparameterize them, okay? But there is some interest in this, because if I go to very large field strengths, okay, then there's some definite lag behind where this localized solution branch sits. This SN1 is far further to the left than the linear instability, okay? So I'm plotting kind of Rayleigh number, okay, driving energy in on the horizontal axis, and then field strength on the vertical axis, okay? So there's a linear instability at mu equals q, okay? So that's T, okay? So then I've got instabilities here. I've got uniform patterns that exist kind of in this range, okay? And then the localized things exist in the whole wedge from SN1 up to SN3, okay? SN for saddle node. So I've got a much bigger kind of wedge for where these localized solutions sit, okay? There are some interesting scaling laws associated with these things, which I've sorted out only recently. But the general idea is that we have these two intertwined homoclinic snaking curves again, but they're pushed way more subcritically than the uniform pattern, okay? So the uniform pattern is here, there's my linear instability, and then these localized solutions are all the way back at smaller Rayleigh number, okay? Smaller Rayleigh number means larger field strength, so sort of this picture, if I take the picture on the right and I go from right to left, that's the same morally as going here from left to right, okay? So as I go along in this evolution where I start the next calculation, or Blanchflower started the next calculation at the finishing point of the previous calculation, then just up the field strength a bit and then up the field strength a bit, you see little patches where you have kind of continuous smooth evolution, okay, of these equilibrium states, and then these sudden jumps, okay, and the flow realigns. And then you have a different number of convection cells. And that corresponds to walking down this set of stairs, okay, you hit a saddle node bifurcation when you've got a kind of 5-roll solution, and then you drop off that saddle node and you restabilize on a different branch. Okay, so you have that similar kind of tiered structure because we've taken this little strip of localized solutions and kind of spread them out. Okay, these solutions are fully nonlinear, so even extracting those scaling laws from my non-local Ginsberg-Landau equation was a small challenge. They sort of, as you up the field strength, they get progressively higher. You know, they're more vigorous, and they are much smaller structures, so one can rescale in various ways. And there's an approximation technique which is good enough to extract the scaling laws by taking my variational structure, okay, and not minimizing over all functions, okay, or over some function space, but taking a parameterized family of functions, okay, and then computing just something that's stationary with respect to that finite number of parameters, okay. This is done routinely in the world of nonlinear optics, and through useful conversations with various people, I've made it useful here, very useful indeed. So this gives you, it's an approximation technique, but it somehow is good enough to capture some of this leading order asymptotics if that's all you want. And in fact, then so I have to choose a family of functions, okay? So I chose a family of functions which are top hats, okay? They're 0, and then they're constant and non-zero, and then they're 0, okay? And that's good enough. I tried some more complicated things, but you know, something that's just jumps between two levels is kind of good enough just to extract the scaling laws, okay? And so going back to this bifurcation diagram, there are sort of two slopes here. There's a slope 2 for SN1, okay, and a slope 1 for SN3. So there's this whole wedge opening up in parameter space between these two curves, and the numerical work was pretty good, and the theoretical predictions are for 2 and 1. So I'm quite confident about that. So in my final couple of minutes, I just want to play with the problem in a slightly different direction. So I played with it once by adding on this extra diffusion equation that gave me a new branch in my dispersion relation that I couldn't ignore. Okay, I couldn't ignore it, and in a particular distinguished limit, it became extremely useful. Okay, there's another way of playing with this, which is to bolt on some more terms, and in fact, this extended version of Swift-Hohenberg is natural for a particular double limit where I'm thinking about a pattern-forming instability that occurs at long wavelengths. Okay? Then one can rescale the variables and say that there are terms involving exactly two derivatives which come in, but they don't necessarily have any connection with each other. So in one particular case, if beta is 2 alpha, then this combination preserves the variational structure we saw before, but not necessarily. Okay? And then one has 3 competing quadratic coefficients here, b, so unfortunately it was called s before, alpha and beta. Okay, so one question is, you know, what are these normal form coefficients? Which regime am I in? Okay, am I in the kind of Q4 positive case where I kind of understand life, or am I in Q4 negative where people haven't found a kind of natural collection of problems yet? So anyway, there's some handle turning through the multiple scales analysis that can go on, and then through various other reductions to be able to compare the spatial dynamics normal form with what comes out of the multiple scales reduction. And I have a Q2 quantity, so am I supercritical or subcritical, which is now quadratic in these various parameters. Okay, so I have a quadratic form here. Okay, Q2 is just, you know, some quadratic combination of all these parameters. And if I plot the set where Q2 is 0, I'm solving for a quadratic form. Okay, so in my parameter space, this is one condition on 3 variables, so I have a 2-dimensional surface. Okay, that 2-dimensional surface turns out to be a connected one-sheeted hyperboloid, and I've plotted it here. These are 2 views of the same object, okay, just to convince you that it does indeed look like a hyperboloid. And I've colored it according to the sign of Q4, okay, to see whether including these non-variational effects gives us access to that second part of the bifurcation structure, and it does. Okay, so there are red regions where Q4 is positive, so kind of previously we've been working close to this white dot, okay, and then in the blue regions Q4 is negative. So if I want to investigate, you know, all the dynamical possibilities, I just need to kind of plot a path for my parameters from one to the other. Okay, So if I just do a couple of snapshots of this, okay, so this is 1.8 is a kind of standard number for producing the homoclinic snaking that we've seen before, so that's the pair of intertwined curves here on which localized states lie. Okay, and then this is a blow-up of a blow-up, looking close to this saddle node bifurcation on this point. Okay, there's a kind of secondary bifurcation branch that's well known towards what people call a ladder solution or a rung solution of an asymmetric localized state. So instead of being even symmetric about the center or in this case up in the middle or down in the middle, but even symmetric in both cases, this is an asymmetric version of that, which just drifts very slightly because I'm not in a variational context. And this happens past the saddle node bifurcation, so I kind of don't worry about it. Okay, I'm stable all the way up to the saddle node bifurcation. As I increase alpha further, a quite natural thing happens, which is that this bifurcation point comes down past the saddle node, and I see that I've got a reduced region of stability. Okay, so this is now a kind of traveling instability. I don't have a stationary localized lump anymore, but it's just, you know, drifting in a very gentle fashion. And it can do this because I'm not variational. For more extreme values of this non-variational parameter, I can also find an oscillatory bifurcation of my localized solution, which is of standing wave kind. Okay, so I have a little localized state here. This is x on the horizontal against time on the vertical. Okay, so I'm looking at a little kind of one-peaked localized solution that's just kind of pulsating. Okay, in a very gentle time periodic fashion. And this is an instability that wasn't, you know, dreamt of in the variational context that we had to begin with, but in other contexts it's perfectly possible, and there's some scope by sort of moving away from the variational problem in a careful fashion to understand where these things come from. So I'm going to stop there. This is a brief summary of what I've talked about. Thank you very much indeed.
Would it be interesting to look at time-dependent R? Because experimentally, you don't just turn on R, you have to ramp it up. And I think if you quench into the unstable regime slowly, you would have a different selection mechanism.
Yeah.
And then viscous fingering experiments, you can stabilize solutions by varying R even in a fully nonlinear regime.
Yeah, this is all still very, it's not very dynamic, really. It's all just to do with, you know, what is the equilibrium set and how is it connected. So I think when you do dynamics, there are plenty more things that come in. Yeah.
Yeah, I mean, in the first part of your talk, you had your homoclinic snake there,
Yeah.
kind of in the shadow of your main hysteresis loop.
Yeah.
So how would you get there if you had an experiment and you
You just perturb locally. So if I start at 0, and I just kind of start with an initial condition that's dragged up towards the other solution locally, and then it comes back down, that'll stabilize on a localized state.
Is that how it happens in experiments? So you actually give it a kick and it actually finds one of these solutions?
Yeah.
Okay.
So the step up, step down profiles that you were looking at, what were the spatial extents of those?
It's a parameter, and then you minimize over the parameter.
Yeah, but again, the spatial extent in X of those plateaus, they were much larger than order 1?
At which point?
You were in deriving your scaling law.
Right. So it was still, I was on the long length scale. So you choose a family of solutions. So that sort of top hat profile is parameterized by the height and the width. And then I have two parameters, and I go and minimize over things that look in that shape and to see where I have an equilibrium structure that's, you know, close to being that size. And those parameters, the values of those parameters, then I kind of hid, because what I really wanted was what that implied about the relation between the Rayleigh number mu and the field strength q. Okay, to be able, what was the kind of the minimum mu at which I could sustain that as a structure. Okay.
So you could perhaps construct those as uniformly valid asymptotic expansions with that as your leading order approximation.
You could tell me what the next terms look like. Yeah, I could do, I suppose. So there's a...
Because the reason for saying it is that in addition, when you put this non-variational term in, you basically have the possibility of two types of defect. The the step down and the step up.
Yeah. Say that again.
So that's too detailed. So that one doesn't matter.
I'll talk to you afterwards. How about that?
Other questions? Thank you very much again.
Thanks.